That's fine. And now you can see. So this is what? What type of equation is this? What type of equation is this? It's a differential equation, right? So vector fields represent differential equations on manifold. What is the solution of this differential equation? If you start from some x node and you solve this differential equation for some time t, what's the solution?
Exponential.
Is that point that you want, right? Exactly that point that you want. So how do we get the flow map? Well, go and solve this differential equation. Let's have a very quick example. So, examples. First example, x on Rn, x of x is just a constant vector A. Constant. Please solve the differential equation x dot equals large x, which is A. Can we solve this differential equation? Little x dot equals A constant. What's the solution? What's x of t? What's that?
T.
Your initial point plus AT, right? This is the flow map. So it's phi t large x x naught. So we get the flow map by solving the differential equation. So the flow map, it's a map on the manifold. It takes any point and returns you another point by flowing along that vector field for time t. Well, let's make it more serious. X gamma Rn defined as x of little x is a matrix A times little x. Can you tell me immediately what is phi t x naught? What's the solution of this differential equation? X dot equals Ax. Anybody remembers? Ax to 70A or 200A.
E to the power
To
A.
the AT. This is a matrix times your x naught. So your flow map takes your point and multiplied by a matrix. The resulting point is the point that you flow along your vector field by time t. Okay? Any question about the flow map? I mean, it's the solution of this differential equation, or the flow map is the map that takes you any initial point and flies along some vector for some time. Okay? So, back to the theorem. I'll do it up, but let's finish this. Two vector fields, this is the last theorem we're going to have. P and point in the manifold. Define gamma, a curve on the manifold from 0 to some time. So this is a curve, right? By gamma of 0 is the point, and gamma of t is the following. Look at this, just bear with me for a minute, please. Flow along x from your point for some time t. Actually, sometime is square root t. Okay? Sometime. If t is 4 seconds, then we fly here for 2 seconds. The result is a point on the manifold, right? Phi square root t y. What's that? This is composition of maps. It's as if I'm doing. Okay? So I started with p, fly for some time along x, I got a point. I will start at this new point and flow along y for some time t. It's the same time. Then I'll do the same, but now I'm going to reverse the order. I'm going to do it for, I'm going to flow along negative x. You know, you remember we roll, pitch, and then negative roll? So whatever the result of your point, I will flow along negative x now for some time. Then, finally, the other way around, negative y. This is all the givens of the theorem. The then statement is here. Then gamma dot 0, the obtained velocity vector at 0, if you do this flowing, is simply the Lie bracket between x and y. Which means, practically, if you like a Lie bracket and want to do it, You have two actuators, right? Turn on your actuator for some time and turn off the other. Then turn on this guy and turn off that guy. And then turn on this guy negative and turn off that guy. Turn on this guy negative and turn off that guy. The end result is a motion along the knee bracket direction. It's exactly the same way as you do in parallel parking. In parallel parking, we have two actuators. I can move forward and backward my car, and I can do steering. But I cannot do sideways, I cannot do that. So how we do it? Move forward, right? Turn left. Reverse now, move backward, turn right. The end result is pure side motion, okay? So this is how we do the knee bracket. Okay, see you next time.
Can you put the blackboard?
Oh yeah, sure.